Find the minimum cost to meet the demand. In this problem, there is a demand, D, of 10 units of water, which must be satisfied by one or more of three water sources, 1, 2, and 3. For each source, there is an associated cost function for the water itself, and also a cost function to convey the water from each source towards the demand. Notice that there is no cost to convey water from source 1 to the demand. Also note that link Q2 shall convey the flow from both sources 2 and 3. Before we begin the dynamic programming algorithm, we'll try a few simple solutions to better understand the costs. Since the total demand is 10 units of water, let's guess that all 10 units of water come from source 1, which means sources 2 and 3 provide no water. After expanding the summation in the cost equation and substituting in the given cost functions for source water and conveyance, the cost equation is simplified. By observation, we notice the flow through reach Q2 equals the supply of water from sources 2 and 3, and the flow from reach Q3 equals the supply from source 3. Substituting these reach costs into the cost equation, the total cost can be written in terms of the sources Q1, Q2, and Q3. Lastly, we'll substitute in our guesses of 10, 0, and 0 for these three variables, and the total cost for this scenario equals 300. If we check the cost for a scenario where all 10 units of water come from source 2, the cost also equals 300, which is also the same cost if all 10 units of water come from source 3. However, due to the quadratic nature of the cost function, the optimal solution will most likely mean that more than one source will contribute to meet the 10-unit demand. Starting from the general form of the dynamic programming algorithm's objective function, we set our objective to minimize the costs, which are added one stage at a time. For this problem, we'll use a backward polling algorithm and minimize with respect to the decision variable. In this equation, n represents the number of stages. xi and xi plus 1 represent the state variable at stage I and stage I plus 1, respectively. The u is the decision variable, small f is the calculated value of the objective function at stage I, capital F, I plus 1, is the optimal objective function value for previously evaluated states xi plus 1, and capital Fi is the objective function value for the current state I. Applying this equation to our problem, we'll set n equal to 3 stages, since there are 3 separate sources of water. We'll define the state variable, x, as the water demand. The decision variable at each stage is the quantity of water supplied by source I. Since only one decision is made at each stage, this is a one-dimensional problem. From the problem statement, we recall the total demand equals 10 units of water. Therefore, we'll assign our initial state variable x1 a value of 10. This represents the water demand before any of the sources have supplied water. After the first source has supplied water, the remaining demand, x2, will equal 10 minus q1. Similarly, state variables x3 and x4 are defined. For all 10 units of demand to be supplied, state variable x4 must equal 0. Next, we'll substitute in our given cost equation for little fi as the objective function to be minimized. Now we'll begin with stage 3. Since the value of the final state variable x4 must equal 0, then we can disregard any final term, for there is only one possible ending state. From the problem statement, we were provided the cost associated with water supply from source 3, as well as the conveyance cost through reach 3. By inspection, we realized the water supplied by source 3 must equal the flow through reach 3. Therefore, after making the substitution, we solve for the optimal objective function value at stage 3, which equals 2 times the quantity supplied by source 3 squared. Also, from our state dynamics equation, since x4 equals 0, then x3 equals the supply from source 3, as well as the conveyance through reach 3. Next, we're ready to move on to stage 2. From the problem statement, we can look up the costs associated with water supply at source 2 and conveyance through reach 2. And from our previous calculation, we know the optimal objective function value from state x3. After substituting in the values, we next need to represent the supply from source 3, Q3, as a function of the supply from source 2 and conveyance through reach 2, which equates to the flow through reach 2 less the supply from source 2. After writing out the quadratic equation and simplifying, and then taking the derivative with respect to the supply from source 2, and set the value equal to 0, we find the optimal operating policy dictates that half the flow through reach 2 comes from source 2. From observation, the flow through reach 2 equals the supply from source 2 plus the supply from source 3. From earlier, we already know the supply from source 3 equals state variable x3, and x3 also equals x2 minus the supply from source 2. After making the appropriate substitutions, we find the flow through reach 2 equals state variable x2, which makes x2 equal to 2 times the supply from source 2. To solve for the optimal objective function value at state x2, we'll substitute in half the flow from reach 2 for the supply from source 2, and after simplifying, the optimal objective function value for state x2 equals 2 times the flow rate through reach 2 squared. For stage 1, we'll look up and plug in the supply cost and conveyance cost and optimal function value for state variable x2. Next, we'll solve for the flow through reach 2. From earlier, we know x2 equals x1 minus the supply from source 1, and we already computed x2 equals the flow through reach 2. After the substitution, we'll write out the equation, simplify, and then take the derivative with respect to the supply from source 1, and after setting that value equal to 0, we find the supply from source 1 equals 0.4 times x1. With all stages complete, we can return to our state dynamics equations and solve for each state variable and the quantity of water supplied at each source. Since x1 equals 10, q1 equals 4, which makes x2 equal to 6. Since q2 equals half of x2, q2 equals 3, which makes x3 equal to 3. And since we know x4 equals 0, we can compute q3 equal to 3. Plugging these values into our cost equation, we have a minimum cost of 120. When reviewing the possible solutions, the answer is B. An alternative way to find the cost is to to solve for the optimal objective function value at stage 1. After taking the derivative and finding q1 as a function of x1, we can substitute in 0.4 times x1, which simplifies to 1.2 times x1 squared. Since our state variable x1 equals 10, our optimal objective function value equals 120.